These are notes on logistics curves, the very last thing we need to cover in AP Calculus BC. Logistics curve is a curve that follows a pattern something similar to this. It occurs a lot in nature. A lot of times, most of the example problems deal with animal population. If we introduce a certain number of animals to a new environment, they have as many resources as they want, so the population begins to grow almost exponentially. But it can't just grow exponentially forever because there's only a limited amount of resources. So as the population size goes up, at some point, the population is going to begin to approach the maximum amount of population that would be allowed given its environment, that would be possible given its environment. So a curve that looks like that is given by a differential equation. It can be in either one of these forms. The second one's a little bit more common, especially on the AP exam. I've seen it like this a lot more. Notice dy dt is only in terms of y. There's no t's in my equation here. Y is my variable. That's the population size. K is a constant. It's determined by how quickly this rises or falls. And we'll talk a little bit about what L is here in a minute. The equation for this curve is given by the general solution. P is equal to L over 1 plus BE to the KT. P equals L over 1 plus BE to the negative KT. B is not the initial population, but it's determined by the initial population. And then some important characteristics about this logistics curve. The first, the function is always increasing. It's always going up. As t approaches infinity, the population size approaches L. And that is the same L that is in these equations here. It's the same L as what's right there. So basically this y value that it's approaching is L. That L is called the carrying capacity, the maximum capacity that could be reached by the population. And then the point of inflection, this point right here, and this is important, is at a y value of L divided by 2. And that is regardless of the initial population size. If we introduce 50, and this is at 1,000, this point here is going to be at 500. It'll follow that shape. If we introduce 400, and this is at 1,000, it's going to start to grow quicker, but this point of inflection would still occur at 5,000 or 500. It's always half of 1,000, regardless of what the initial population is. If we bring in 600, you're not going to be able to see the point of inflection, but it would have occurred if it could go back negative in time. It would still be at half of 1,000. So the first example we're going to take a look at, a little bit more involved than most of them that we'll do, but let's take a look at one that kind of works through everything here. So this one says, a state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. They give us an equation for the growth rate of the elk population. It says the PDT equals KP times quantity 1 minus P over 4,000. Notice my differential equation is only in terms of Y. Y is P in this case. Notice also P is on the outside of the parentheses here, and it's also on the inside. Those are all good signs that this is a logistics curve, which it is. Notice L in the formula is right under the Y. L is 4,000, which makes sense. The environment can support no more than 4,000 elk. So our L value is 4,000. Part A asks us to write a model for the elk population in terms of T. So we want the general formula for population. So population equals L, which we just said was 4,000, over 1 plus BE to the negative KT. So notice there are two constants we need to solve for. We need to solve for B, and we need to solve for K. So we need at least 2 points. We are given 2 points. We know at time 0, we have 40 elk, and at time 5, we have 104 elk. So let's start with at time 0, we have 40 elk. So if I plug in 0 for time and 40 for number of elk, my equation would look like this. E to the 0, which is 1. So I can now solve for B. Multiply both sides by 1 plus B. Divide by 40. Subtract 1. And I get B equals 99. So plug 99 in for our B. Now we need to figure out K. After 5 years, we have 104 elk. So plug in 104 for P, and 5 for time. And we should be able to solve for K. So multiply both sides by the bottom there. Divide both sides by 104. You could also distribute the 104 if you wanted. Gives me 38.462. Subtract 1 gives me 37.462. Divide by 99. Gives me 0.378. To solve e to an exponent equals something else, we're going to take the natural log of both sides. Natural log of e to the negative 5k is just negative 5k, is negative 0.9718. Divide by negative 5 gives me k, which is what I was trying to find, 0.194. So we can go back into our equation here and plug that in. 4,000 divided by 1 plus 99 e to the negative 0.194 t. That is our answer to part A. We're not going to do part B here. It asks us to graph a slope field. We need to do that. Part C, use the model to estimate the elk population after 15 years. We're just going to plug in 15 for time into our equation here. I get 628.5. Let's round to the nearest elk, 629. Part D asks us to find the limit of the model as t approaches infinity. As t goes to infinity, if I plug in infinity here for t, I get e to the negative infinity. Times 99. E to the negative infinity goes to 0 times 99 is 0, so 4,000 divided by 1 is 4,000, which makes sense. That was our limit of the logistics curve. Let's take a look at number 7 here. Number 7's from a practice AP exam that was released. It says a population y changes at a rate modeled by dy dt equals 0.2 y times quantity 1,000 minus y. Again, dy dt, y is on the outside and the inside. This is a logistics curve. It says t is measured in years. Where t, what are the values of y for which the population is increasing at a decreasing rate? So we need to recognize this as a logistics curve. A logistics curve looks like this. This is 1,000. This point right here is half of that, 500. Increasing, it's always increasing. At my slope is getting bigger until 500. I want it to be increasing at a decreasing rate. Now my slope is getting smaller. So from 500 to 1,000, y values from 500 to 1,000 only. And number 6, I don't know why it's called number 6. Says, let P represent the population of rabbits in a field. The rate of change of the population is given by dp dt equals 0.008 P times the quantity 5,000 minus P. Part A says the initial population is 60. What does the population approach as t goes to infinity? As t goes to infinity, we are going to approach the limit. Notice this one is not 1 minus p over L. This one's L minus p. Either way, the limit is 5,000. Whether we introduce 60 rabbits or 700 rabbits, the population is going to approach 5,000. As t goes to infinity, what does the rate of change of the population approach? As time goes to infinity, my slope is going to 0. Part D wants us to write an equation if P of 0 equals 100. Our population equals our limit, which is 5,000, over 1 plus b e to the negative kt. This one's nice because it does give us k in the formula here. K is the value out front here, 0.008. Going back to, notice k is what's multiplied by y out front. P of 0 is 100. So if I plug in 0 for time and 100 for population, I should be able to solve for B. Dividing both sides by 100 gives me B equals 49. So part D, P equals 5,000 over 1 plus 49 e to the negative 0.008 t. And finally, part E, what will the population be when the number of rabbits is growing the quickest? Logistics curve looks like that. Population is growing the quickest. Notice the slope is the greatest at its point of inflection. What will the population be? It's half of the limit, which would be 2,500. So those are logistics curves. We will practice many more of these prior to taking a test or quiz on them.